Hello everyone, myself Tulsi Pawar, Assistant Professor in Physics, SPC Government College अजमेर। MSc भौतिकी के सॉलिड स्टेट फिजिक्स पेपर के अंतर्गत आज हम पढ़ रहे हैं सुपर कंडक्टिविटी में फ्लक्स एक्सक्लूजन या माइजनर इफेक्ट। It was assumed that the effect of a magnetic field on a superconductor would be same as in a metal. However, in 1933, Meissner and Ostenfeld measured the flux distribution outside tin and lead specimen, which has been cooled below their transition temperature while in a magnetic field. They found that the transition temperature, the specimen spontaneously become perfectly diamagnetic, cancelling alignment and flux inside even without they been cooled in a magnetic field. This experiment was the first to demonstrate that superconductors are something more than the materials which are perfectly conducting. They have an additional property that merely resistance-less metals would not possess. A metal in the superconducting state never allow magnetic flux density to exist in its interior. That is, inside a superconducting material or metal, we always have B is equal to 0. Whereas inside a merely resistance-less metal, there may or may not be a flux density depending on the circumstances. When a superconductor is cooled in a weak magnetic field, at the transition temperature, persistent current arise on the surface and circulate so as to cancel the flux density inside in just the way as a magnetic field is applied after the metal has been cooled. This effect, whereby a superconductor never has a flux density even when in applied magnetic field, is called Meissner effect. Suppose a magnetic field of flux density B is applied to a superconductor. In order to neglect demagnetizing effects, we consider long superconducting rod with the field applied parallel to its length. An applied magnetic field of flux density Ba produces in the material flux density equal to mu r Ba, where mu r is the relative permeability of the material. Metals other than ferromagnetic have a relative permeability which is very close to unity. So, the flux density within then due to the applied magnetic field is equal to Ba. However, as we have seen, the total flux density in a superconducting body is 0. This perfect diamagnetism arises because surface screening currents circulate so as to produce a flux density Vi, which everywhere inside the metal exactly cancel the flux density due to the applied field. It means Pi is equal to minus of Ba. A rod-shaped superconducting specimen therefore behaves like a long solenoid with circulating current that creates a flux density exactly equal in magnitude but opposite in direction. So the flux density due to the applied magnetic field. To create a flux density of minus Ba, the magnitude of the circulating surface current per unit length must form the ordinary solenoid formula J is equal to B upon mu naught. This is the diagram showing the magnetic behavior of a superconductor. Diagram A to B shows a specimen become resistanceless in the absence of a magnetic field. And diagram C, magnetic field applied to a superconducting specimen, and E and F specimen becomes superconducting in applied magnetic field, and diagram G shows applied magnetic field removed. In other words, J is equal to HA, where HA is the applied field strength. We can however describe the perfect diamagnetism in another way, because we cannot actually observe the surface screening currents which arise when a magnetic field is applied. we could suppose that the perfect diamagnetism arises from some special bulk magnetic property of the superconducting metal. And we can describe the perfect diamagnetism simply by saying that for a superconducting metal mu r is equal to 0, so that the flux density inside B is equal to mu r B is 0. However, we do not consider the mechanism by which the diamagnetism arises. The effect of the screening currents is induced in the statement mu r is equal to 0. The strength H of the applied magnetic field is given by HA is equal to BA upon mu naught, and the flux density in a magnetic material is related to the strength of the applied field by B is equal to mu naught HA plus HM, where M is the magnetization or intensity of magnetism of the material. The magnetization of the superconductor, in which B is equal to 0, must therefore be M is equal to minus HA, and the magnetic susceptibility chi is equal to minus 1. This is the maximum value of the superconductive, maximum value for the susceptibility of a diamagnetic. In this sense, a superconductor is a perfect diamagnet. However, it must be noted that superconductive is not only a strong diamagnet but also a new type of diamagnetism. Thank you.